Let me start by reminding you of one of the main things that I wanted to prove at the end of last lecture, which is the Slice-Bennikin inequality. And I also realized I didn't really motivate why one might care about something like this. So I mean, what's cool about this is it's telling us something about. I mean, the proof of this sort of the. It's telling us something about how the rigidity of this tight contact structure can give us topological information, which is something very special. So what I didn't make clear in the definition of the self-linking number that I gave, this braid theoretic definition of the self-linking number, is that this is really some kind of relative Euler class of the contact structure, and so it's really the fact that the contact structure is tight that is allowing us to prove this, but somehow that's all missing from the proof, but it somehow is being captured by all this algebra, and that's kind of an amazing thing. Anyway, okay, so let's quickly prove this, and then I'll start talking a little bit about the SL2 representation theory. Okay, so here's really the proof, and this is the proof given by independently by Plemenevskaya and by Shimakovich. So really, the observation is that if sigma hat is a braid, is a closed braid representing this transverse isotopy class of naught, then actually it turns out that these canonical Lie classes. Get a better piece of chalk. So it turns out that the canonical Lie class associated to either orientation, either braid-like orientation, is a deformation of the Plemenevskaya class. So this comes just from the definition of this canonical Lie class, which I haven't given yet, but let me give it now. So this canonical Lie class, remember, it's associated to this to markings of the totally braid-like resolution, and in this case, so what it turns out is that this class is gotten by marking each of these with V minus plus V plus, V minus minus V plus, alternately as you go from outside in. So depending on the orientation, I'm not going to worry too much about which orientation corresponds to what, but for one of them, it's V minus minus V plus, tensor V minus plus V plus, tensor, etc. And then for the other orientation, this is one of them. And then the other one is where you just start with the plus first. Okay, so now what do I mean by these canonical Lie classes being deformations of this Plemenevskaya class? Well, I just mean that it's this. So if you boil out the tensor product, you get the Plemenevskaya class plus a bunch of terms that have higher J, plus a bunch of other J homogeneous terms that have higher J grading. Right, so for example, take the first one of these. So this is really the Plemenevskaya class plus terms that have higher J grading. Because when you replace a V minus by a V plus, it just raises the J grading by 2. And so what this is telling us is that the J grading of Plemenevskaya's class, which we essentially define to be the self-linking number, is actually equal to the J grading of this canonical Lee class. Because remember, we're assigning to an inhomogeneous chain the minimal J grading, which is, of course, less than or equal to the J grading of the corresponding homology class, because the corresponding homology class is the max over all possible J gradings. And as we said, this is S of k minus 1. And now we appeal to Jake's theorem, which is telling us that this is less than or equal to twice the 4-ball genus of k minus 1. There's the negative Euler characteristic of a surface showing up. And there it is. Okay, so it's just a really nice little proof of that once you know the Rasmussen theorem. Okay, any questions about that? So it's really just the fact that somehow the canonical Lie classes are deformations in a certain sense of the Plemenevskaya class. Uh-huh.
How was this slice bending inequality originally?
Right. So what Lee Rudolph did. How was the slice-Bennick inequality originally proved? Let me not try to remember. I do actually think I can remember. I just can't right now in front of everybody. But yeah, I'll once I remember, anybody can ask me. But at the moment, I'm okay. All right. So let me now tell you a little bit about representation theory, and we'll actually see that that you can kind of obtain these canonical Lie classes in a nice way with respect to this SL2 representation theory. There's a nice SL2 representation theoretic interpretation of these canonical Lie classes, which is kind of one hint that representation theory is interesting and relevant to topology. Okay, so since I'm going to talk about SL2, and this is a group of topologists, let me just quickly remind you of everything that we'll need to know about SL2. So again, here for today now, my field is C, just because the SL2 representation theory is easiest there. Okay, all right, so SL2 is a three-dimensional Lie algebra. So it's generated, so the underlying vector space is very naturally generated by three basis elements that we call E, F, and H. And of course, we need to specify a skew commutative bracket. So the bracket of E and F is H. The bracket of E and H is negative 2E. And the bracket of F and H is 2F. Okay. And now any representation of a Lie algebra is a map, is a homomorphism from your Lie algebra to the endomorphisms of some vector space for which this bracket goes to the commutator. Okay, so the canonical, the defining representation is two-dimensional. I mean, after all, this was originally traceless 2x2 matrices. So the defining representation, so this is a two-dimensional representation. And it's very naturally, there's a very natural basis for this two-dimensional representation, which ends up being an eigenbasis for the operator h. So with respect to this particular basis, h is given by a diagonal matrix. E, oh, I think I want it actually to do it the other way. Sorry, v minus v plus. E raises v minus to v plus and kills v plus. And F lowers v plus to v minus and kills v minus. Okay, so this is the defining representation. And why am I always losing erasers? Okay. And the point here is that h of v plus v minus, so these are eigenvectors of h, and the eigenvalues are plus or minus 1. Okay, so these eigenvalues of h are often called the SL2 weights. Okay, so v plus has weight 1 and v minus has weight negative 1 in this terminology. Okay, so now I've told you about one finite dimensional representation of SL2. Here's one more. So there's also v0. So let's call this one v1, because the highest eigenvalue of eigenvectors with respect to h for this representation is 1. V0 is just the trivial representation. And this is the one where your homomorphism from your Lie algebra to the endomorphisms of a one-dimensional vector space. So I'll just say 1D vector space. Sends E, F, and H all to 0. Okay.
Elliot, if you're writing v minus and then v plus is the matrix for h.
Oh, maybe I wanted it to be the way that it was originally. Yes, I do. Sorry. Yes, thank you. Thank you. Okay. So that's really all we're going to need to know about SL2 representations for this talk. So now let's talk about the vector space underlying the Khovanov-Lee complex. As an SL2 representation. So it's going to be quite a simple one. So when I say the vector space underlying the Khovanov-Lee complex, I mean just this vector space, but forgetting about the differentials for a moment. Just thinking of it as being just being a graded vector space. Well, what are we going to do? Well, the first thing we need to do is regard our braid closure So remember, I said at the very beginning that if you have a braid, you can take its closure in S3. But sort of first what you're doing is you're taking its closure in the solid torus and then embedding that solid torus in S3 as the complement of the braid axis. So really here, actually I wanted to use a different color. Is we're thinking about this braid closure as being in D cross S1 inside of S3. But really it's natural to regard this solid torus as being really a thickened annulus, because an annulus is really where the diagram lives. So if you just mark a single point, extra point, which is sort of where the braid axis is puncturing the plane, and then you maybe mark another point just to sort of represent this point at infinity. You can put in this marking, and that really is specifying the link. Sorry, I want to do it here, but then of course it goes to all of the complete resolutions as well. So regarding the braid closure as being in the solid torus, can be that information can be gotten by just putting this extra marking on your diagram. And now once you have this extra marking, what that allows you to do is look at all of your component circles of your resolutions and see whether or not they hit this extra arc an odd number of times or an even number of times. If odd, then that component is has non-negative winding number around the central X, the central marking, and if an even number of times, then it has zero winding number. So you have the so-called trivial circles. So let's call them T circles in a complete resolution. These are the ones where the T intersect this arc gamma. Let's call it gamma. Is even. And the non-trivial circles NT are the ones where the intersection with this arc gamma is odd. And now what we do is just assign to each trivial circle. So remember, assigned to each circle, we have a two-dimensional vector space, and then we're taking a tensor product of those to get the vector space associated to a resolution. So now let's just make this two-dimensional vector space into an SL2 representation in the sort of maybe obvious way. So you assign to a trivial circle just two copies. So this is a shift in the J grading. Two copies of this trivial representation. And to a non-trivial circle, you associate, either V1 or V1 dual. And these are actually isomorphic as SL2 representations, but the point here is that we need to pick up a sign somewhere, and this is how we do it most easily. So this is if an even number of circles separate T from what I call X over there, So as you're going from inside out, you label them V, V dual, V, V dual. So this is if an odd number of circles separate from, right, this is NT from X. So this resolution here would be labeled V1 tensor, V1 dual. And the thing that I want to point out is that if you have two Lie algebra representations and you take their tensor product, then you have a tensor product representation of the Lie algebra. And the way that it works is by the Leibniz rule. So now take the tensor product representation. Tensor product. So how does this work? So if you have a Lie algebra representation on two vector spaces V and W, and now you have some element of the Lie algebra, then you extend linearly from the action on these decomposable vectors as X acts on V tensor W plus V tensor X acting on W. Okay. So now we just see how SL2 acts on the vector space underlying this Khovanov-Lee complex. Associated to each non-trivial circle, you have this non-trivial representation of SL2, and associated to each trivial circle, you have two copies of the trivial representation of SL2. And what you might now notice is that at this point we get a third grading. So we get what we call a K grading. So we have an I grading, which is the homological grading, a J grading, which is this quantum grading, which was very important in Rasmussen's S invariant definition. And now we have this third grading called the K grading. And this is the SL2 weight space grading. And it's just the sum of the pluses minus the sum of the minuses on the non-trivial circles. So extend via the normal way you extend on a tensor product via addition from this. K of V plus minus is equal to plus or minus 1 if it's marking a non-trivial circle. And 0 if it's marking a trivial circle. Okay, so it's actually a very easy SL2 representation. Let's use this. So then it actually turns out, so then it's a little, observation. I mean, it's not even a lemma because we don't really use it for anything. Let's just call it an observation. That for one of the two braid-like orientations, representations. The canonical, let's call it O braid. The canonical Lee class associated to this braid closure, this annular braid closure, is just, well, it's V minus either plus or minus EV minus tensor V minus plus EV minus. So what I didn't say is that for the dual representation, E sends V minus to minus V plus. So that's why we're getting all the same sign now here. And then for the other one, you just get a bunch of minuses in here. So if you think about how the tensor product representation works, what we're saying now is let's just look at one of these, that you can really write this as a sum over divided powers of, I shouldn't use K. So if sigma is an n-strand braid, then we have this Plemenevskaya class, which has weight negative n. And what we're doing is applying powers of E divided by I factorial. So you can work out why this is an alternative way of writing this. It's definitely not immediate, but and in the other case, you just have a negative 1 to the I in front. So the other one would be same thing, but with a negative 1 to the I in front. So this is one place where the SL2 representation theory is really showing up in some way. Okay. So now, of course, what you want is for me to tell you something that it says about topology. And so I'll try to at least say something that it says about topology. Okay, so first, actually, a warning. You might be tempted to believe, from what I said, that that either Khovanov homology or Lee homology inherits an SL2 action, and that is not the case. And the reason is that it's sort of the naive way that you would inherit an action from something like a Lie algebra on the homology of a complex, if you have an action of the Lie algebra on the vector space underlying the complex itself, is if this action commuted with the differential, or at least it did up to homotopy. That's kind of what you would hope. And that is not the case for either the Khovanov differential or the Lie differential. So let me just say that neither the Khovanov differential nor the Lie deformation or their sum commutes with this SL2 action. Even up to homotopy. So we do not get an induced SL2 action on the homology. However, the sort of interesting thing is that each of these differentials, the Khovanov differential and the Lee deformation, actually decompose in terms of SL2 weight space gratings into two k degree homogeneous terms. So, however, so let's just call this a however, because I'm not really going to give the argument, but where the degrees of these summands are homogeneous in both J and K. So this has degree 0, 0. So these are the JK degrees written below the summand. This is 0, minus 2. So we already said that each of these was degree 4 with respect to the J grading, and one of them is degree 0 with respect to the K grading, and the other is degree 2. And it actually turns out that if you look at either one of these, so a little bit of thought will convince you that a necessary condition for one of these differentials to commute with the SL2 action is that it preserves the SL2 weight space because it commutes with H. So in particular, they're going to need to have 0 degree with respect to this K grading, which is the SL2 weight space grading. And in fact, not only does it do that, but it actually commutes with the whole SL2 action. So both of these differentials commute with the SL2 action. And it actually turns out that if you take the homology with respect to this one, you get what's called annular Khovanov homology or sutured annular Khovanov homology, which is a nice conjugacy class invariant. It's a conjugacy class invariant. And so what I'm saying is that SL2 does act here. And in fact, SL2 acts on the homology with respect to this Lee, this part of the Lee differential as well. But unfortunately, it doesn't seem to be an invariant of anything topological. All right. Oh, and I should say this was originally defined by Asaeda, Shevitsky, and Shikora, and further studied by Lawrence Roberts and a number of other people. Okay.
Sorry, so maybe I missed this, but why consider acting probably, by the reason of, why not
Uh-huh.
just look at bigger intricate,
Why SL2? So you'll have to ask Tony, who was the one that first suggested that annular Khovanov homology should carry an SL2 representation. But then when you start to think about, when you forget that it should come from somewhere and you just look for it, like it has to be an SL2 representation. I mean, this K grading was known before, and it's sort of, once you sort of think that K grading must have some representation theoretic content, this has to be the way that the representation works, and it's an SL2 representation. It's not something else. I mean, maybe there are other interesting things that act, but this one is like staring you in the face. Like, you can't miss it. Although we did for like 10 months. Was it 10 months? it was many months.
Are those two papers still the best sources for annular Khovanov?
Yeah, I think Lawrence Roberts' paper is where I first learned about it, and it's a good read. Yeah. Okay, so now we have now I've sort of introduced the gradings to you slowly. We have the cohomological grading, this J quantum grading, and now for annular links we have this K grading on the Khovanov-Lee complex. And so this may come out of just like left field. Let me. So what I've done here is drawn a picture of the Khovanov-Lee, the annular Khovanov-Lee complex. Let me explain this picture. The annular Khovanov-Lee complex of this simple link, braid closure, and the way that you should map the objects that you see over there to objects that you see over here is that all of the generators at this vertex will be marked with a solid dot over there. The generators at this vertex are marked with a star. Generators at this vertex are marked with a square, and this with a heart. Okay, so there should be 2 hearts, 4 stars, 2 squares, and two dots, if I've done everything correctly. And I've tried as well as I can. Sorry, this is probably really small for you, for the people in the back. I've tried as well as I can to sort of cluster things at the corresponding. So the one thing I need to explain is that the gradings I'm using are J and J minus 2K, which will probably sound really weird as choices, but I'll explain why in a second. And it should actually be kind of obvious that the complex looks kind of nice using these 2 gradings, in the sense that it looks symmetric about the slope 1 line through the origin. You can see that there's this sort of symmetry in the complex. And in fact, D minus is sort of going to phi plus here. And then you have this phi 0, which is also symmetric with respect to to this reflection symmetry.
Where's the other dot? By the star?
Yes, I think so. It's either here or here. Yeah, it's here. Okay. So this is no accident. This is really coming from a natural involution on the annular Khovanov-Lee complex, which you should really think of as manifesting a symmetry inherent in SL2. So if you notice, if you exchange E with F and H with negative H, then you sort of get the same thing. And that's really reflected here. There's a symmetry with respect to the K gradings. And if you think about it, these lines of slope 1 here have constant K grading, and the lines of slope negative 1 have constant J minus K grading. And in fact, if you think about it, the SL2 action preserves J minus K. So you'll see SL2 acting along these lines of slope negative 1. And E would raise this guy to the sum of these guys, or maybe the difference, and raise each one of these to this. Okay, but the point is that, so there exists an involution, so here's a remark, is that there exists an involution theta on the Lie complex of an annular link, so in particular of a braid closure. Actually, I should probably put that notation in there so we don't forget. And it exchanges Well, it sends d0 to itself as well as phi 0. But it exchanges the roles of d minus and phi plus. Okay. But what should really get us excited is that when we use this j and this j minus 2k grading, actually this complex becomes not just z filtered, but z plus z filtered. If you notice all of our differentials, so if we were to write down the j minus 2k grading of each of these terms, we always get something which is monotonic and positive in both gradings. And that's really the reason why we're choosing j and j minus 2k. So we already know that each of these terms is monotonic in the j grading, but it actually turns out it's monotonic in the j minus 2k grading as well. So this is 0, 0. D minus is 0, 4. Phi plus is 4, 0. And phi 0 is 4, 4. Okay. So what this suggests, if one is familiar with the epsilon invariant in Heegard-Fleur homology, so since this Lie differential is monotonic, with respect to these two linearly independent gradings, it has the structure of a Z plus Z filtered complex. So CF, the epsilon invariant. In Knopfler homology, due to Ajvat, Stipschitz, Szabo, but really as reinterpreted by Chuck Livingston. And that's where I would recommend you go first if you want to see the connection between what's done over there in that context and what we're doing here. So the key idea here is that if you have a Z plus Z filtered complex, then you get a whole intervals family of R filtered complexes, which allow you to, from the same chain complex, extract a number of gradings, an intervals family worth of gradings. So, so this allows us to, so the picture you should have in mind is that if you have some complex and the differential is monotonic with respect to, so we saw a similar type complex in Adam's talk, but the differentials were going down instead of up. But if you have such a complex, if you now project it to any line of positive slope, you get an R-filtered complex, which, like general R-filtered complexes, are probably not good enough to extract, well, definitely not good enough to extract gradings from. But these particular ones, since they're finite dimensional, the gradings are well ordered. So you can play the same kind of game. So the point is that you get a family of R filtrations. and hence a family of Rasmussen invariants. One for each t in the interval, real number t in the interval 0 to 2. Okay. Oh.
How do you promote z squared to r?
So I'm actually going to explain it in a second, but the picture you should have in mind is that you take this two-dimensional complex and you just project it to various lines, and you see that these arrows will project positively, or sorry, non-negatively. As long as the arrows are going non-negatively in both of these linearly independent directions, when you project them, they'll still have that property. That's not exactly how we define the grading, but it's a good. It's basically it. Really what we do is we take a grading which is called the J minus TK grading for t between 0 and 2. And you just show that each of these gradings, this Lee differential is monotonic with respect to each of those gradings. So define the JT grading of a distinguished basis element to just be the J grading, So these distinguished basis elements are homogeneous with respect to J and K. So you can define it as J of X minus T times K of X. And now, so for each T between 0 and 2, this Lie complex is now R filtered, and R filtered good enough to define with plus some additional properties, just coming from the finite dimensionality of the. Good enough to extract gradings on homology classes. Okay, so it's still the same complex. It's still the same Lie complex. You still have canonical Lie classes associated to the different orientations. But now you just have a bunch of different gradings you can define on these canonical Lie classes. So that's what we're going to do. So I'll make a definition, give a theorem, and I should have said at the very beginning everything that I'm talking about today. I should just write it over here or over here. This is joint with Tony Licata and Stefan Wehrli. So everything in this lecture, this SL2 action, this was work that we did together. So here's the definition, and it's exactly what you might expect. So let's define. So let's let sigma be a braid, and T a real number between 0 and 2. So we're going to define the DT invariant of the braid closure, but now regarded in the solid torus. To just be the JT grading of the homology class, of either homology class associated to either braid-like orientation. Okay, this is either braid-like orientation. information. And I mean, hidden behind here is a similar theorem to Jake's, or a similar lemma to Jake's, that the JT gradings of the two canonical classes actually agree. Okay, and the theorem is that this is a braid conjugacy class invariant. It's a braid conjugacy class invariant. And you can see that it essentially agrees with Jake's S invariant at t equals 0. The symmetry will tell us that it also essentially agrees with Jake's invariant. I mean, it's just one off from Jake's invariant at t equals 2. It turns out that because of the symmetry, we have a symmetry across the t equals 1 for these invariants. But they give us some nice information about special link cobordisms. So this is really what's new. So let's say this is part 1 of the theorem. Part 2 of the theorem is that if we have two braid closures, sorry. So if F is a braided cobordism, and I'll explain what that means. So a braided cobordism is just braided link cobordism. So a braided link cobordism is just a link cobordism whose regular slices are braid closures. So if F is a braided link cobordism, from the closure of sigma hat to the closure of sigma 1. And again, we're going to want to, so with, let's say, A1 index 1 critical points, odd index critical points, and A0 even index critical points. So notice for the even index critical points, the new circle in the case of a 0 handle will be braided, and you can only delete circles which are braided. Even index critical points. And we want for which every component of F has boundary in both sigma 0 and sigma 1. Then the absolute value of the dt invariance, the difference of the dt invariance, will be bounded above by A1 minus A0 times the absolute value of 1 minus t. Okay, so that's just a formula. Why should you care, or why would one care? Okay, now if you'll give me I know I only have 1 minute, but if you'll give me 5 minutes, I'll actually tell you something interesting. Maybe interesting. I'll at least tell everybody about a theorem of Lee-Rudolph's that every low-dimensional topologist should know.
Is that 1 minus t multiplying just a0 or a1 minus a0?
No, just A0. Okay. So the corollary here is that we get a bound on the so-called band rank of a braid conjugacy class. So what's the band rank? Well, if you looked at the first problem from the exercises, a band is just a conjugate of an elementary Artin generator. So, for example, it looks like this. Here's an example of a band, and I'm drawing it so that it really looks like a band. So the point is, if you see, so here's a quasi-positive band. Here's a positive elementary Artin generator, and then you have some braid going towards it, and then the conjugate of the braid. But the point is, if you look at the sort of braided surface, what you're really seeing is a ribbon immersed surface that's gotten by sort of pushing this through this disk out and then through that disk and then hooking up with this band. So the point is, if you now do an elementary saddle-cobordism here, you can sort of pull this out and you get a surface with a single a surface from the original braid closure of this band to the identity braid closure with a single odd index critical point. And what's interesting is if you realize your surface as a product of these bands, then you have a very nice ribbon immersed surface in S3 corresponding to that. And so this band rank is very closely tied to the complexity of such surfaces, because you're asking how many of these index 1 critical points do you need in order to get from your braid closure to the identity braid closure. And of course, this is if one knew somehow that all ribbon immersed surfaces could be realized in this way, then we could really study ribbon immersed surfaces in S3, which of course are understanding those are a crucial component of understanding these big conjectures, like, well, the big conjecture, the slice ribbon conjecture. But if we knew that, then somehow this band rank would be quite relevant. Luckily, we do know that because of this amazing theorem of Lee-Rudolph, which should be better advertised than it is. So let me do that now. So here's the theorem. So let's let F be a ribbon immersed surface. And again, all my surfaces are orientable. Orientable surface. Ribbon immersed orientable surface in S3. and F is isotopic to a so-called banded braided surface. By which I mean the obvious surface, ribbon immersed surface that you get by realizing your braid as a closure of these bands and constructing the surface with one disc for each strand of the braid and one band for each Artin generator anchoring one of these one of these components of the band product. So what I want to point out is that a corollary of this theorem so corollary of this theorem is that if you have a knot in S3 which is ribbon, so in the standard sense of ribbon, that it bounds a smoothly embedded disk in the 4-ball with for which the radial function has no critical points of index 2, so no maxima. So it turns out, with a little bit of thought, you can see that being ribbon is the same thing as bounding a ribbon immersed surface in S3. So K bounds a ribbon immersed surface in S3. So if K is ribbon, then what Lee-Rudolph's theorem is saying is that K, so there exists an index n braid representative of K with band rank n minus 1.
So it's a disk. A disk.
Yeah, thank you, yeah, that's what I meant to write and say. K bounds a ribbon immersed disk. So of course there's the slice ribbon conjecture, which is that if you're if you're sliced, then you're ribbon. So if you bound a smoothly embedded disk, then you bound a possibly non-isotopic disk, which happens to be ribbon. And this conjecture has been around since the 60s. So this kind of suggests a possible, completely speculative way of approaching the slice ribbon conjecture. Namely, if you could find some kind of bound on the band rank, and you could understand how it behaves under stabilizations and destabilizations, then you could extract from it a ribbon obstruction using Lee-Rudolph's theorem. So that's sort of the posteriori motivation for everything that I said before. Okay, thank you.